So again, if you have not yet clicked on one of the links in the chat, either the download of the PDF version of the notes or the Amplify version of the notes, please do so that you have a copy. And of course, this will be available after class as a filled-in version. All right, today we're going to be talking about exponential functions and how they are on STAR, how to use Desmos to work to make them easier to solve, things to make it easier for you to get these questions correct on the STAR test that is coming up in December. Today we're going to analyze exponential situations so that we can write exponential functions, and we'll know we have it when we can make predictions from an exponential situation. All right, guys, so we actually do have exponential growth and decay all around us every day. We see these graphs. We just don't really think about what they mean in terms of math. So, for example, COVID cases, when we first started tracking them, so it says days after March 1st, 2020. So just keep in mind that this day 0 here, when we're reading it, is March 1st, 2020. Okay, not the beginning of time. And then we had steadily increasing, but it was increasing exponentially. What that means is instead of, let's say, I go out, I'm sick, I infect one other person, they infect one other person, they infect one other person, or I infect 2 people and that's it. Okay. And then, so that's just something to keep in mind. If we are like one after another, it would be a straight line. But the way things like that work is that, for example, I go out, I infect 2 people. That means now we have 3 people infected, right? And then they each infect 2 people. So now that's 4 more people. So now 7 people are infected. And then they go out and infect 2 people. So that's 8 more people. Now 15 people are infected. So that's how this works. It's really, really fast growth. Right? Credit card debt also grows exponentially quite frequently. Part of that is due to the fact that we have what is called compound interest. So interest makes it go up faster. But our growth in credit card debt over the course since 1970, looks like that's when they started marketing this market trend. Years. Okay, so we have different parts of the exponential function. So we can see our f of x, that's our y, that's the total amount we can expect to find. A, which is the first number, that's our additional amount, that is our initial amount, sorry, or our y-intercept. So for example, in my example where I was sick and I infected 2 people, the initial amount is we just had me. I infected 2 people. So our initial amount is 1. All right. And then our ratio, right? That is how many people am I infecting? Every person I infect 2 people. Okay. Well, then they infect 2 people each. So now that's 4 more, right? And then they infect 2 people. Okay. So it's getting bigger and bigger and bigger because that was 8 more. And then the last part of the exponential function is the time. How long did we do this? So let's say this was day 1, day 2, day 3. And the day you start on is day 0. Okay, always. So how much time has passed since we started collecting data? All right. How many times have we doubled? How many times have we tripled? How many time periods have passed? Okay. So it could be years, it could be minutes, it could be months, it could be weeks, it could be anything. All right, so now what we're going to do is talk about what is called an asymptote. All right, there is an important line called an asymptote in every exponential function's graph. link. Okay, so we have the asymptote line. Let me go ahead and get in here. We want to go ahead and see what happens when we press play on that activity. This is slide 8. So if you guys haven't clicked the link yet, it is in the chat. So let's click play on that and we can watch what happens. Does Mario ever go below the x-axis? Okay, so if we click on that, does Mario ever go below the x-axis? And go ahead and give me a thumbs up for yes and a thumbs down for no. Does he ever cross the x-axis? What do you think, guys? All right, well, Mario never goes below the x-axis. Okay, so let's take a look back here. So no. A key feature on every exponential function is called an asymptote line. It's a horizontal line where the graph never touches. It gets closer and closer, but it never actually touches it. Now, asymptote line does not mean it's a horizontal line. It's in this function only. So it's actually just a line that the graph never touches. Okay, so I'm actually going to cross out that word. In exponential, it's always horizontal, but in other functions, it can be vertical. Okay. So the equation to the asymptote is always going to be x equals something. So what line does it never cross? In this case, it never crosses x equals 0. Y equals 0. I'm sorry. I didn't mean to say x. Okay. Y equals 0. So looking here, it says the asymptote line can also help us determine what the range of the function is. So if the graph never ever goes below y equals 0, it's never going to go below this line here, then we know that y will always be greater than 0. And it's never going to touch 0. Okay, it never actually reaches that line. Never reaches it. So keep that in mind. Since it's not going to touch the y equals 0, we won't have the line underneath. Okay, so it never reaches or crosses it. Okay, so let's look at this graph. This is 10, y equals 10 times 0.5 to the x. And we want to know if this is growth or decay. Now, the first thing it tells us to do is look at the b value. Well, at this point, we haven't really talked about what the b value means, okay, to remind ourselves. So in this case, we can see that this is less than 1. If it is less than 1, it is decay. Okay. If b is less than 1, we can look at the graph and also see that it's decay. So if you look at the graph here, it's clearly going in a downward direction. Okay. All right, so nice. We want to know what is the y-intercept on this one. The y-intercept is, of course, the first number. That's the a value. So where does the graph start? If we look at this graph, we can see that it starts here at y equals 10. So our our y-intercept is located at the point 0, 10, right? And here they only want the y value, so you would just write 10 or type 10. And then what is the asymptote line? Okay, well, on this one, it looks like it is never reaching 0. It looks like it's going to be our x-axis. So that's going to be y equals 0. Now, the reason y equals 0 is that we're never, ever going to get to 0. We're never going to actually have an answer equaling 0. So what I'm going to do here is I'm going to show you a few things. Let's say I had y equals, we're going to just put 2 times 2. And then what we're going to do is we're going to raise that to the negative 35. This number is incredibly tiny, but it is not 0, okay? So as we increase, even as our exponent gets negative, we're still not getting to 0. So if you look here at the example I'm showing you right now, no matter what I do, or no matter what my negative is, it's just going to get smaller and smaller, but it's never going to quite be 0, okay? Morning. I don't know when you said that, but oh, it was only 2 minutes ago. Okay, cool. Sorry about that. So we'll never get to 0, and that's why that's our asymptote. All right. Okay, give you a moment to catch up. All right, so let's go ahead and look at the next one. We can look at the graph. We want to know, is it exponential growth or decay? Now, in this case, it looks like it's going downwards, okay? But look at the way it's curved. So let's look at the b value here. Look at that b value. If you remember, in the last slide I said, and I forgot to write it down, my apologies, that if b is less than 1, it's decay. If b is greater than 1, it is growth. So in this case, our b equals 2. 2 is greater than 1, so therefore, we're looking at some growth. Okay, so this one's actually going this way. Okay, and that's because we started at negative 7. What's our y-intercept? It's right here. That is 0, negative 7. And then the asymptote line here, we can see again, it looks like it's not going to get to 0. So y equals 0 should be the correct answer. I don't have that one in my slideshow, so you can skip the one that I don't have if you want, unless you want to try it. Weird. Okay, well, let's look at it. So let's look at this one. We look at our y value, or our b value. It's greater than 1, so this is growth. Y-intercept is 4. Oh, look, it put a little smiley face. That's so cute. I wonder how they did that. I'm gonna look at the code for this later. Sorry about that, guys. Here's the one we were actually on. Decide it was decay. The y-intercept is -7. That is so cool. I really want to know how they made the smiley face appear. And y equals 0. All right, so let's look here. Before we graph it, we can graph it and look at it later in a moment. But is the function y equals -8 times 2 to the x growth or decay? Well, again, if we look at our b value, we start at our b value. I'm going to change from yellow. We can see that our b equals 2. And since 2 is greater than 1, we're looking at growth. Remember, our y-intercept is our starting value. So that's going to be -8. The point would actually be 0, -8. And then in this case, the asymptote is still going to be y equals 0. Because we can't get to 0. Now let's take a look at the graph and see what it would look like. It was y equals -8 times 2 raised to the x power. And we can see the asymptote here. It's never going to get closer. And this is another way to look at it. Look, if you take your cursor and you drag it along the graph and you look at that y value, it's never actually going to, it looks like it's 0, but if we were to zoom in first, they're just rounding, okay? If we actually ran x is -25, let's do that. So I'm going to change this as f of x. Okay. And let's say if we wanted to find f of -25. Notice how that's not 0. That's just a very tiny number, okay? What this is let me go ahead and copy that just so I can see it. Paste. All right, so this is a very small number. So we have -2.38415,791 times 10 to the -7. So this number is actually 4, 5, 6, 7, 1. Okay. So 1, 2, 3, 4, 5, 6, 7, 3, 8, 4, dot, 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 dot. Okay. So this number is really, really, really tiny, extremely tiny. But what it is not is 0. It's very, very, very close to 0, but it is not 0. All right, so let's see how they handle these on the STAR test. I like how it the Spanish does still translate star with the 2 A's as Estrellas. That's funny. Anyway, researchers studied the population of a town over time and modeled the data using an exponential function. The initial estimated population was 48,000. Okay, so remember, I'm going to go back up here to my color coding real quick. Yeah, A is my initial. Apologies, guys. So initial population was 48,000. Then after the first year, the population was 50,400. If the population of the town continues to grow at this rate each year, which function can be used to model the population X after the years after the researchers began their study? All right, so the first thing we want to know, okay, is we know the initial population. So we're going to look for ones that have 48,000 as the first number. Okay, remember, initial is our starting value. Okay, it is going to be, remember, in our y equals ab to the x, that's our start. So that tells me I don't need to worry about either of these two. Okay, now what we need to know is what was the ratio. So again, we know that after 1 year, okay, again, year is a unit of time. So time is x. So the 1 should be the x. Since the 1 is not the x, I want to look at this equation b. Okay? This is just so I can look at it and see if it makes sense. Not b, a, sorry. I eliminated b because of what it had there. My apologies. A. All right. So what I'm going to do is I'm going to put the equation that I think it is. And that is y equals 48,000 times 50,400 over 48,000. Is that right? 5400, yep. And we're going to raise that all to the x power. We don't actually need to see the graph, all right? But what I want to do is see the table. Does this show the same first value? And it does, okay? So our answer is A. It's good, the same population after 1 year. So it's what we were looking for. It's going to be good. All right, so the number of students who participated in sports was 317 this year. Okay, so this year was 317. Each year, the number of students who participates in sports increases, that's our rate, by 4%. What function can be used to model the number of students participating in sports after X years? And of course, highlighting in black isn't going to work, but there we go. Okay. So first thing we want to do is this is our starting, all right? This is our initial. If you see an increase of a percentage, that tells you you're going to look at exponential. Okay. So what that means is this one right here, B is linear, D is linear. A and C are both exponential. A and C are both exponential. Now, we can want to know if it's increasing by 4% each year, okay? So what that means is when we represent percentages, remember they're as fractions. I left out a T and then accidentally erased everything. That works. Remember percentages are fractions. Okay, you're good, Briley. Out of 100. So 4% is 4 out of 100. Right? That is a 4 out of 100 increase. Originally, we get to keep the original 100%, okay? Because a 4% increase means that if we have 100 students in year 1 and we increase by 4%, that means we're going to have 104 students the second year, okay? If we represent that as a fraction of 100, so that's percentage for the next year, that is 1.04, okay? 100% as a fraction is just the number 1. So the answer to this one is C. Right, this one right here looks like it says an exponential function is graphed on the grid. Which function is best represented by the graph? So let's go ahead and do some process of elimination first. We can see we're above the x-axis and we are going down from right or left to right, so it is decay. That means B is less than 1. Okay, and remember our formula is y equals, or f of x equals, a times b raised to the x power. All right, so we want b is less than 1. That tells me that the answer is not C, because b in this one equals 1.25. And this one has b equals 25. So I was fascinated by the question for a moment. So what we could do here is we could just graph these two and see which one looks better. Let's go ahead and delete everything we had from before. I always recommend deleting stuff. All right, so we had 0.25 raised to the x. And that does have a starting value of 1. There we go. That one matches the graph. If we look at the other one that they had 2 times 0.5 raised to the x, and that one starts at 2. Now I could see that in the equation, but the problem I was having was seeing it in the graph properly, okay? Because it looked like a 1, but I wanted to make sure. Okay, so again, this one has an a value of 2, and we want an a value of 1. So our answer was A, which is 1 times 0.25 raised to the x power. All right, looking here, number 26 here, we have the table shows the value in dollars of a motorcycle at the end of X years. We can do this one in Desmos as well. We're going to do a regression. So first thing you're going to do is add a table in Desmos. And then you're going to enter the number of years. We have 0, 1, 2, and 3. And then we have 9,000, 8,100, 7,290, and 6561. 6,561. All right, graphing those. Now we can look at our options here. We could see that the starting value, where y equals 0, is 9,000. And we can see that there is some exponential decay here. So if we look here, this is going downwards. So the best answer I see here, and I'm hoping is going to be the answer when I check, is going to be G, right? That's the answer I want to check. However, it's possible it's one of the others. But what we're going to do is we will click this button here. It says add regression. And we are doing linear. If we look here, we can see the R value is pretty good. But let's look here at an exponential regression where we get our R squared equals 1. Okay. And also our answer choices were all exponential. So we're going to do an exponential regression. We get 9,000 times 0.9 to the x, 9,000 times 0.9 to the x. Make sure you have that copied into your notes. All right, number 11 here. All right, take a look at this and see what you think. I'm gonna give you a couple moments. All right, so one thing we can see is what is the starting value is 0, or sorry, not 0, just more than 25, but it's 25.5. So we're gonna look here and we're gonna see which ones are, okay, so remember our function is A times B to the X. And again, reminder, A is our initial and B is our rate. Okay, this is a percentage or a ratio. We can see that our starting value, our initial, is 25.5. So we can see the ones that start with 25.5 are B and D. Those are the only ones that can still be possible. All right. For the rate, remember, when B is less than 1, it's decay. When B is greater than 1, it's growth. Okay. And so we can see that it is going down. Remember, decay means to get smaller. So we're going to look for a B less than 1. So on option B, our B is 0.6. And on option D, our B value is 6.10, or sorry, 12. So the answer we are looking for here is going to be B. G of x is equal to 25.5 times 0.6 to the x. Now, do you want to check it? You should. We always should check our work. 25.5 times 0.6 raised to the x. Okay, we can see the graph. I actually think it would be best to just take a look at this table. With 1 15.3, 1 15.3 is 2 9.18, 2 is 9.18, so it matches. All right, let's see if we can come up with some that we can eliminate here. We have some points on the graph. Actually, we could do that, but we're just going to do an exponential regression. Let's make our life easier. So I'm going to delete this, and I'm going to add a table, 2, 3, 4, 5, 6. All right, and then we get 36, 54, 81, 121.5, and then 182.25. Click the Add Regression button. We're doing exponential functions. Again, if you're on star, it's not going to say, oh, this is an exponential function. But if x is an exponent, it's an exponential. And we have 16 times 1.5 raised to the x. So 1.5 is the same as 3 over 2. So our answer is F. All right, go ahead and get that copied into your notes. All right, my computer did something crazy. All right. Next one. Oh, right. Paste. I almost forgot to put the answer in there. All right, number 33. Okay, it says, in the year 1900, the total number of metric tons of copper produced in the world was 495,000. Each year since 1900, the total number of metric tons produced has increased on average over the amount produced the previous year. Since which function models the total number of metric tons of copper produced in the year that is X years since 1900? All right, so let's look at the problem again. Remember our formula for exponential, and I believe this is on your star formula chart. It's just not color-coded. We have A times B raised to the X. In 1900, we had 495,000 metric tons of copper in the world. And then we are increasing by about 3.25%. All right. So what we're going to do is look for one. We don't want these ones because the x is not an exponent. Okay. In here, we want to look, we're looking for an increase. Remember, if b is greater than 1, it's increase or growth. And if b is less than 1, that's a decrease or decay. So if we look here, we want an increase. A is the only option written in exponential form that gives us an increase. We also know that if we have 100% over 100, and we have 3.25 over 100, if we were to add those in Desmos, we would get 1.0325 as our B value. All right, and that looks like it is our last slide on here. So I want to wish everyone a good luck when you take the test. It is after Thanksgiving break. This is our last boot camp. And there is a break next week. Make sure you are ready for review these notes, review these videos. This will be on YouTube as well before the test. Have a good day. Bye, guys. All right, you're dismissed if you want to take off. You don't